Alright, folks, I'm gonna be with you in a couple of minutes and we're gonna start the stream. We've got a little bit of analog design today, so hope you enjoy that. Hello folks, how are we doing today? Let's see. Yep. Let's take a look at the desk. Oh, I don't know, we're probably not gonna dwell at the desk right now. There's a bunch of stuff going on, but anyway, mostly what we've been working on recently is kind of a bit of a side project of my co-founder mostly. Yeah, I'm helping him, like basically building some hardware for him. So this is one part of it. You might have seen this on our Instagram. This is partial built logic board for a new thing that's basically gonna it's basically an Arduino, let's say, with some MIDI on it. That has a built-in delta sigma ADC. Oh, interesting. With a backlight you can see the split grounds here. Yeah, that's pretty cool. Yeah, so anyway, what we are going for with this thing is basically trying to see how much of precision ADC we can get, or rather like how precise basically of an analog input we can get from a touch sensor, from a resistive touch sensor like this one here. Yeah, this is actually like a disassembled touch controller that has this. I don't know if I can get the whole thing in the frame somehow. Maybe it's quite long. Let's see. Kind of. So anyway, yeah, it's a long touch strip with basically analog. So there's a module for that comes with this thing, and a rack module that you can put in your case and connect to this. So originally this had a USB port in here, but it didn't actually use a USB interface, just I don't know, the physical connector, and that was used to plug into the module. Or connect the module with the touch strip. So basically what we're trying to do here is mod this thing to be more precise and so mostly this is gonna be a part of MIDI controller. So it's not gonna be just the touch strip. We have other touch surfaces on it for and basically that's gonna come in a form of guitar-like instruments. So yeah, my co-founder basically wants like this kind of guitar you can plug into your rack and use that as a controller, right? But since this is gonna be MIDI, which we decided to do it with MIDI because, well, basically that way we can just stream all the control surfaces values, all the control values for a single for a single USB wire, and also get power to the device from the USB host. So yeah, I mean, we could make a dedicated module for something like that, but and have a bunch of wires going to here. But I kind of prefer doing this in like a digital domain, so that gives us more, more ways to play with that and calibrate stuff and perhaps do some more complex stuff. So we sorry, let me see if I can get the chroma keying a bit better. It's 2. It's making me transparent. Let's see. I guess that's kind of better. Yeah, brought on the noise, but anyway, yeah. So this is the main controller board for this. It has a couple more components to it. So there will be like mechanical switches and like kind of AUI to use switch programs, and then all the touch surfaces. We have a joystick with my output and that as well. So all that stuff gonna be connected to this. Now, what we've yeah. So basically, to facilitate all of that, we want to have a precise ADC for for reading this touch strip. And now with MIDI, we can get basically 14 bits of precision. So unless we do MIDI 2.0, which yeah, probably wouldn't make a lot of sense since pretty much nothing supports that. So yeah, so we will do MIDI with the like extended CC. So in MIDI there's basically a way to specify 14-bit CCs, but by setting two CC values together. Let me see if I can get some spec on screen for that actually. What was it called? High resolution? High resolution MIDI CC. Sure. I mean, whatever they say here is pretty much correct, I think. So yeah, you basically take a CC number and then add 32 to the number, and that gives you the CC for the higher and the lower part of the word. Right, because like the typical USB CC is 7-bit, right? So just 127 discrete values, and with 40, I guess you can get 16,000 something. Okay, so now we have this touch strip. I mean, I don't know what kind of physical limitations there are actually to this. We are kind of, but I mean, so that's just mostly a continuous, resistive surface here, right? And depending on where you touch it, this acts as a potentiometer that will give you a resistance, based on the distance from the ends of the strip. Right, so there will be some noise in here probably, and it's probably not gonna be perfectly linear. It kind of, I think that just depends on the distribution of the conductive material along the strip, but it should be pretty close or close enough. Now, mostly we are dealing with noise in the electronics. So let me see actually if I can get a schematic for this part. So yeah. 1 second, please. Yeah, there we go. So this is the control board. So we basically got our SAMD here, and then that's the ADC. So let's say microchip part. That's Sigma Delta ADC. This one here. So this is a 24-bit converter. Yeah, say it's low noise. Okay, fair enough. So the specs is, if I remember correctly, it's that it's 1 LSB, basically level of noise. So we didn't get it quite to this level, although I think this pretty much follows the reference circuit they give in this spec. Let's see. Yeah, it was somewhere in here. Yeah. No, that's. Let's see. This thing here. So, I mean, it's pretty simple. So, one thing we are doing is we are using differential input here, and yeah, there is a couple of things we are doing to try to keep this low noise. So, first of all, we do differential connections between the converter and the analog front end here. So this is like a prototype of the analog front end that basically connects to, or will connect to, the touch strip itself, and then yeah, there is an op-amp here that serves as a preamp, and then it generates basically a positive and negative differential signals. Then we also have a shielded twisted pair, basically it has the cable here. I mean, the cable itself is not very long, but it's I guess something around 1 meter long. Yeah, so there's a shielding here, and the signal wires are twisted. Then there's a couple more things we do, which I'm gonna talk about in a couple of minutes, probably. Yeah, so anyway, looking at this as this reference schematic for the converter here, I mean, there is like, I think, surprising really. So you have to give it an external reference, and for that, since we didn't really care about absolute voltages, just you know, the ratio of you know, the touch position, you know, voltage to the reference. We just use the VCC as reference, and then in a couple of places we use VCC divided by 2, basically half of VCC to well, basically to have the offset for for the differential, right? So when the negative is below half VCC and positive is above, yeah, and then this and this analog section we are building here is gonna, you know, convert that. So yeah, so this basically this is the model of our touch strip, right? And then it the one end is connected to ground and the other is connected to VCC divided by half, right? Which itself is generated here. Okay, so our reference voltage is just 3.3 volts. We're also using this supposedly low noise regulator from TI. We did use that on KRS2 for analog parts or analog sections. And yeah, that seems to be performing okay. So there was a bit of work done to basically try to filter out noise from the USB view bus from the supply voltage or from the supply rail. So there's a huge cap here. It's this big electrolytic here. Yeah, then we have the farad bit on the input side and this low noise regulator. And this is a good part and it's pretty cheap. So yeah, and there's a separate voltage supply for the microcontroller and all the digital stuff, right? And the UI in display and buttons, which I don't have here to show you right now, but yeah, that's another part that connects on the basically on the digital side. Yeah. So yeah, and this looks again pretty much like the reference schematic here. So yeah, so the VCC is yeah, the 3.3 comes from this analog voltage rail, and yeah, there is a separate digital supply. So this is the same 3.3 volts that we generate for the microcontroller. And here they do for basically extra filtering, they put this 10 ohm resistor before the coupling capacitors, right? So in addition to your the coupling caps, you have basically an RC filter made with this resistor, right? So generally you have your track impedances, right, coming from the power supply to here, right? So you have your LC network basically generated by or created by the tracks and the cap. Yeah, but they, you can put an extra resistor to basically get even better filtering. Yeah, and the of course you get a little bit of voltage drop here, but and that part doesn't consume a lot of current, so it doesn't really hurt us that bad. Yeah, but anyway, all the readings are supposed to be based on the voltage reference here, so that's what we are mostly worried about getting clean, I suppose. So in this schematic, they also have an op-amp to drive the reference input. We don't really do that because we are running the reference straight from yeah, this is the input here, straight from the power rail. Now this is a little bit different than what's actually on the board, because originally I had VREF also generated with a voltage divider, so that was half of 3.3 volts. Yeah, but that just turns out that's not what we wanted, so it's just the full 3.3 volts. Well, the judgment is still out of what is correct here. Actually, I'll still gonna do some testing, but if I recall correctly, when I set this to half of 3.3 volts, I just limited the range. So yeah, I made a mistake basically somewhere. If calculating those voltages. So the thing is, this is all differential inputs, right? So even though like the value or the voltage single end, or like the voltage coming out from the strip is from 0 to 3.3, right? Then we also have to like basically add the other part of the differential pair. So we just need to make sure all the math works out. Anyway, yeah, so yeah, let's take a look at the schematic again. Right, so here again they also support, I mean, I guess this could be either single-handed or differential, but yeah. At least the way this is drawn, I guess it kind of suggests we are doing differential here. Yeah, anyway, there's like an RC filter on the input, and we have that as well. So this is the input coming from the analog section. So that's basically those two connectors here, right? So one is dedicated to the touch strip, and we have position as well as a pressure channel. The position and pressure are a little bit different in how that touch strip works. I mean, one of those is more like a potentiometer, right? So you basically get a voltage divider depending on where you press. That's gonna determine the voltage division. But the pressure touch strip, that's more like a variable resistor basically. So we have to have some extra circuit to basically either do a voltage divider ourselves, or convert that resistance to voltage in some way. Yeah, so I guess we can maybe look at it a little bit today. I'm probably not gonna be streaming a lot today because I feel kind of shitty, honestly. But yeah, just wanted to do a quick walkthrough of what we have here so far, and yeah, where this is going basically. So let's see. Yeah, so the inputs have a filter here, and that's pretty much very important because you want to filter out your high frequencies just to and it's an anti-aliasing filter mostly in terms of function, right? So basically you want to cut out your frequencies above you want to cut out frequencies above the sampling frequency, because then they would get reflected down, and you would get some spurious low frequencies in your digital signal. So yeah, and we also gonna probably put some extra filtering on the analog section as well. It's generally probably like the more filtering, I think higher frequencies we do, the better, right? We just need to make sure the cutoff isn't too low, so we still get we still have a good responsiveness from the sense. But yeah, anyway, otherwise we are not expecting any high frequency signals, so we want to get rid of them. Yeah, and our filter is here currently. So right now that this is actually 100 ohm, and when you cap and so the filter or the filters let's see if I can get a little bit more lit here. Yeah, so this here is the ADC, right? And between the connectors and the ADC there are like tiny resistors and capacitors. Now, one thing that is kind of sensitive here is when we did use ceramic caps for those one use. Now, with that, you kind of have to be careful because, well, the ceramic caps can be piezoelectric, so basically they can convert sound and vibration into current, and yeah, that's definitely what we don't want on our signal path. If we want this to be able to resolve, very tiny voltages. So that is something basically you need to test for, but since the impedance here is not gonna be that large. Yeah, so again, this is gonna be all 100 ohms. Well, I'm gonna change the schematic now, but yeah. So we're moving the cutoff frequency higher, and that's fine because we are still sampling at up to 100 kilo samples per second. So yeah, that would still be very much within that bandwidth, right? And at the same time, I want to keep the impedance of that line small, basically, so that any noise generated here will not affect it significantly. Now, if we there's I'm not really sure if we'll be able to actually test for vibration. That's kind of, I mean, we could whip up some kind of fixture, but generally that's a specialized thing, I think. But yeah, I mean, we can I guess do some basic testing, right? Since this is gonna be on the part of the instrument that that will be held by a person, a guitar-like thing again. We can expect that there will be some vibration present. So yeah, because all those both the logic and all the other parts, right? Those will be just parts that are installed in the body of the controller. Hopefully we'll be able to show you more of that later. We're basically working with with a guitar maker, Lucio, I think is that the English word, right? Who will basically make the body and will integrate those electronic parts onto onto the instrument. Yeah. Okay. So then this ATC is connected with SPI to the microcontroller on the digital side, and there are some resistors. So they say 10R here, but like I think like somewhere in this document they said that they used 100 for testing, or 200. I don't recall exactly. I think they said 100 ohms. So we actually did. This is 47, but yeah, I think in this unit it has 100 ohms on those digital lines, and that's basically to reduce EMI or emissions from the traces, which could couple back onto the analog side. And that actually the digital part, we did actually find out that there is a little bit of noise coming from that. So maybe let me start with how we've been testing this so far. So basically, in order to measure noise coming from different parts of the system, we basically null the inputs here. So in this case, to measure the ADC itself, right? Those differential inputs are just connected together, right? So this would give us like a zero differential voltage, right? And then we basically see what the ADC says. So if there is any noise, inherent to that, to the conversion, that should show up, as well as any offset. And we did indeed see it. And now this is supposed to be 24 bits, right? But if you do differential, that's actually 23 bits, because you also get a sign, right? So you can, for both like negative and positive differences, you get a value, a signed value, basically. So that's 23 bits, of absolute value. Now, the effective resolution is function of that plus or minus the amplitude of the noise, basically. Right. So the goal of those measurements was to basically determine how much resolution we are losing to noise. Right? And if we did everything right, this is up to spec, we should get all our 23 bits minus, I think they say 1 bit LSB of noise is specified. There are some other figures in the spec here. Let's see. So there's a little summary here. So there's the offset specs, and those are all the distortion specs. Let's see. Nice. Oh, there we go. So nanovolts at 16x gain. Oh, there we go. RMS effective resolution. Up to 23.3 bits. Okay. Yeah, so I guess that would mean that you should get below like 1 LSB of noise. Now, we did not get that in our implementation. What we did, the best result we got was 3 bits of noise. So that's still 20 bits effective. Right, and that was just on the converter. Now when we add in the rest of the system, we didn't measure with the op-amp added. And here's the thing, this op-amp is just your basic MCP, what was that, 6604, right? So your basic rail-to-rail low voltage op-amp. And yeah, that has noise. So with that we won't get our 20 bits. So the way we measured this part is, so first of all we also measured with just the cable added. So yeah, there's a little jumper that lets you short out the differential pair. So again, you get like the null differential with the cable added. And that did not change the result in a measurable way. So that's good. And then before the op-amp, there's another jumper to null the input basically. So then you basically get a differential output for a zero, input, right? So as if the input voltage from the touch strip was at 0 volts. Okay. Yeah, and then we can connect the touch strip itself. So yeah, this has a little connector here. Let me get that in frame. Sorry for the noises. So you can plug the touch strip into this analog preamp, and yeah, and the way I do measurements here is I basically take a knob, and this is my finger simulator. So yeah, and then I put something heavier on that to simulate the press. That's probably gonna fall. But yeah, I have this, and now there's the reveal of the maker of the touch strip. So yep, and that's right. That's added upfront for how volume we are using. And now I can get it to stand still. But yeah, you get the idea, right? If you put it in the middle, that's yeah, that's quite stable, something like that, right? And after I do that, I actually get a stable measurement from the touch strip, right? And then we measure basically the amplitude of noise at each of these stages, and that helps us determine how much they contribute to the loss of precision. And yeah, so far this op-amp has been the limit. So what we're gonna do is basically take a very nice and like a completely new part from TI, and that's this OPA 206. So this is like extremely low noise part, and also really low offset as well. Let's see, offset voltage, or so this input current noise is very low, and the figure I'm mostly looking at it is this 0.1 to 10 hertz peak-to-peak figure, right? And that's at 0.2 microvolts. Now, if we were to compare to our regular MCP part, let's take a look at that. Here, I think they should have something in the summary here. Okay, let's see. Oh, actually, yeah, let's just grab the full datasheet. There we go. Oh, for this, I think we need to go to the specs table here. Is it even specified? Oh, there we go. Input noise voltage, typical, yeah, in the 0.1 to 10 hertz range. It's typically 6 microvolts, right? And compared to 0.2 microvolts. So yeah, here's a huge difference here, and that should get us our precision bits back as long as we implement everything correctly. Now this is a little bit higher supply voltage requirements, so at least 4.5. And yeah, this microchip thing that can run at 3.3 volts easily. Let's see what's the, yeah, it's down to like 1.8, sorry, volts. So yeah, so the first iteration of this design, we just assumed we are gonna pass 3.3 volts at our filtered analog supply. But yeah, that's gonna be too low for this, and unfortunately, this is pretty much, I think, like one of the lowest voltages for, like lowest minimum supply voltages for the precision op-amp. They're mostly, like a lot of them require something like 10 volts at least. So yeah, so that's still nice. I mean, if you look at the plots there, you often get even better specs at higher voltages. Right, so this is one thing. So like if you are very close to the rail, you're gonna get some non-linearity. Sorry, some non-linearity. I know I can't speak. Yeah. Oh yeah, and then we get our low frequency noise here. Actually, I'm not sure what's the point of that time domain plot, but I mean, yeah, you can see what the noise looks like, I guess. Yeah, but anyway, like what we care about is it's under 0.2 microvolts. And yeah, actually, yeah, let us do some math here. So we have our 3.3 volt supply, right? And then if we divide that by our resolution of 23 bits, yeah, so that should, in theory, resolve down to 0.4 microvolts, right? 400 nanovolts. Yeah, so the point 2 spec is just below that. Again, in reality, in our implementation, we get more like 20 bits de facto, right? So that's that's still lower volts than than the, what was the spec here, 6 microvolts, I think, right? Arm is nice. No. Where was that figure? Oh no, that's the ADC, sorry. There. Yeah, 6 microvolts. So that would still take away 1 bit of resolution from what we should be able to get ideally. And yeah, actually that was pretty much confirmed by our measurements. And yeah, actually we get even more nuance than that, but that's probably just and yeah, I mean that's just the low frequency, right? Then you get your noise density here. So yeah, I mean, this is of course not like, this is just a prototype built by on this strip board here, but so there's no ground plane, no shielding, no nothing. So yeah, with a better implementation, we'd probably get down to the spec figure. And also there's one more thing that actually kind of screws with the NR adds a lot of noise, and I'm gonna touch on it in a second when we get to our analog section schematics. But yeah, actually I think when we shorted the input or null the input, that gave us something around this 4 bit noise, 4 bits of noise figure. So yeah, that checks out. But then when we add the rest of the system, that's even higher. But so here is the issue I wanted to talk about. So the thing is, with this touch strip, and the only way to detect that you are not currently touching it is the fact that it goes high impedance. So basically, when you release your finger from the strip, that stops acting as a voltage divider and basically opens the circuit, right, between the between your let's say middle pin of the potentiometer and the rest of the circuit. So yeah, because basically when you press down, mechanically make a connection between the conductor and the resistive material. So basically, to tell that you release the finger from this, you have to pull the you have to pull this line to some known voltage level. Otherwise, it would be just floating and give you random measurements. So what I said is maybe not exactly true, in the sense that there is also the pressure sensor. That's like a completely different sensor that's under the position strip. But the thing is, to actually actuate the pressure sensor, you have to press this quite hard. So it is possible to touch the strip gently and get a valid position reading, while the touch strength not being recognized yet. So, and the way the Doppler module that's complementary to this strip works is also like that. So actually, I have a schematic somewhere here, I think. Let's see if I can find it. Yep. So this is kind of a reversed schematic of the trotorium. I had a better drawing of this somewhere, I think. Let's see if I can find it. What the heck? So it's this part on the right here. But actually, this is pretty clever, because you can switch the trotorium between two modes. You either have no hold, which means when you release the finger, that just zeroes out the position output. Or actually, no, not really zeros. Here's the trick. There is a voltage slightly below zero. And this actually took me a second to figure out what's happening here. But you get a diode here that's basically together with this resistor network sets the voltage at this point at negative 0.6, or basically the threshold voltage on this diode. I think actually I assumed it's 0.6. I haven't checked it. It might be, if this is like a Schottky or something, that might be closer to like minus 0.2. Anyway, the main thing is that it's actually not exactly zero. It's like below zero. And then they have this buffer here, basically to buffer the position CV and give you the positions. Yeah, I'll just give you the position CV output with scaling, right? So there is a potentiometer here that lets you scale that the range, basically. But when you flip the hold switch on the module, instead of this this pull down network here, so also like there's this resistor right between the diode and the voltage coming from, so this is basically your and this goes to the middle terminal of the potentiometer, right? Of the position voltage coming out of the strip, right? And again, you have this 10 meg resistor here. Basically, the purpose of this section here is to pull down if a touch strip goes high impedance, right? So if since the touch strip itself, the potentiometer is I think around 10 kilo ohms. I had some notes here. Let's see. Yeah, I measured like 11.2 kilo ohms across the entire strip. So much lower than this 10 meg, right? So if there is a touch recognized by the touch strip, that will basically set the voltage here. Otherwise, it will go high impedance, and then the voltage will be determined by this network here. Now, when you flip to hold on the panel, that changes this behavior by switching to a capacitor here, and this basically turns the behavior from like being set to this negative voltage when the strip is released to basically to hold the value on the strip, right? So this will basically behave like a sample and hold when the touch strip is high impedance, which is pretty clever circuit. Now you also get gate here, and now notice that again you get two different gate outputs in here, and that's because of what I talked about error, right? So the pressure gate is actually less sensitive than the position gate, and the position gate signal is actually generated just by comparing the voltage coming out from this position buffer to 0, right? So when you set that below 0, you get no gate. When you get anything above 0, you get a gate. Right? So pretty cool. And the pressure gate is basically generated from the pressure or derived from the pressure sensor, which again is a completely separate physical layer on this touch strip. So yeah, I mean that's a pretty cool design, but here's the problem with this. So we did start up with something similar, so we also have a pull up. Now here, instead of pulling below 0, I'm pulling to the positive rail, and that's because in normal operation, when the strip is pressed, the value will be in the range of from 0 to half of reference voltage, so half of 3v3. So if we put anything higher than half of 3v3 here, we can basically also recognize that like there isn't this isn't like a valid position volume. And actually, when this goes through, actually this schematic is already modified, but originally I had a second inverting stage from the op-amp just to generate the differential pair. this is gonna be a little bit of difference now when we go to the new parts. So we can also discuss this in a sec. But yeah, anyway. Right now with this prototype here, when there is actually the resistor, I think it's actually like 4.7 mega ohms currently, but doesn't make a lot of difference. What it does, where it does make a difference, is actually this value of this resistor. Is actually also contributing to noise. So there is also the matter of the thermal noise from resistors. Yeah, that's what's it. That's the other name. I think it's usually. I've seen this referred to as just thermal noise. But what's important is the amount of noise depends on resistance. This is a nice example here. Alright, so yeah, basically the higher the resistor value, the more noise density you're gonna get. And a 10 mega ohm resistor is gonna give you significantly more noise than, let's say, a 10k resistor. So actually I think it's a square root of so the noise current is the RMS noise current is proportional to the square root of R, basically. Oh wait, is that right? Oh, I guess that's noise current and noise voltage are different, but yeah, so for noise voltage, right, this is proportional to the square root of R. For the noise current, that's proportional to square root of inverse R. I mean, oh yeah, okay, so that's just the different models. Okay, fair enough. More, I guess, like modeling that as voltage is more useful in that case, right? Since we are indeed measuring voltage. Anyway, yeah, so with the square root of the resistance, you get proportionally more noise. And this is a problem because we do actually get measurable noise with this resistor here. So I'm still considering what to do with that. I mean, see, so there's one big thing about this whole project is actually the best we can do with MIDI is 14 bits, and what I'm talking about here is more like 18 to 20 bits of precision that we could measure with this. What's the point? Well, honestly, the only point of doing this so precisely right now is just to see if I can do it That's the only reason. Because, well, we aren't really currently considering this like volume production product thing. And therefore, you know, we can have some fun with this and see how good of a value we can get. And actually I can use this for other things as well, not just this MIDI controller thing. It may come useful to have like a precision measurement device, because honestly I don't even have a multimeter that can go down to this kind of resolution. Again, this is not designed for absolute measurements, so we're not trying to make any attempts at having perfectly having a perfect voltage reference or zero offset or anything, but still even for like relative measurements, that's a nice thing to have, or just a nice ADC in general, right? Because this can easily be used as an audio ADC as well. Although there we would also have to care more about our THD and figures, nice figures for slightly higher frequencies. Which we did not really consider that much here, but with the design we are going for in this with this new parts we have here, that actually should be also pretty should give us pretty satisfactory figures. Anyway, this resistor here is a problem. Basically, the way I'm thinking of dealing with that is to basically put a transistor here in series, like some kind of entrance. Let's see if I can draw that. Let's see. Let's just use 2N and 702 for now. Although this might have to actually be a P channel. But what the heck? What's going on outside? Yeah. Anyway, something like that. So just we could take this transistor out of the circuit and for measuring the analog value, and then we can plug it in with this transistor to pull up and see if we still have a press or no. Now the problem with that might be that we have a bandwidth limit, right, due to our input filter, so we will have to do that fast enough so that we can sample with a reasonable frequency, and at the same time give the filter time to respond, basically, right, to the step change in voltage. But since like the cutoff of the filter is currently in like hundreds of hertz, if I recall correctly. Let's see. So for a single single RC filter. The cutoff is 2 pi times RC, right? So that's gonna be 1K times 1 micro, so 2 minus 6. So yeah, that's 160 hertz. And yeah, and what we're going for, and also we can tweak that filter, right? Oh yeah, sorry, that's the old resistor value. So now we're gonna actually have not 1K but 100 here, 100 ohms. Yeah, that's more. Yeah, that's the current cutoff. So 1.6 kilohertz, and we are really interested in like hundreds of hertz max, right? So we can oversample here, and yeah, and we should, in theory, I think, have enough bandwidth so that we can switch this in and out while doing the measurements. I don't know, maybe there's a better way to do it. I mean, we could also have a comparator before the filter, like put a separate comparator here and do basically something like what the upper module does. So generate a gate where this goes above threshold, or like in their case below, and then generate a separate signal for the microcontroller to read. And I'm not sure about it. So if we do that, and if that works, I'm sure we could try doing some simulations of that. But I'm probably not gonna do that today because I'm kind of tired, honestly. But yeah, anyway, if we did that, we still need to add one extra signal from the logic board to this to control the gate here. And then I guess this could work. Yeah, so let me give you a quick walkthrough of what's happening on this board anyway, because we talked about the VRF by 2 and this part, this part, which is the position voltage. So now there is also this, which is voltage divider between some known resistor and the pressure sensor. So that's one way to do it, or we could put the pressure sensor in the feedback loop of the op-amp. The reason to do that would be to get basically proportional, so voltage proportional to resistance instead of voltage inverse proportional. Get like 1/R measurement. Now, which is better? That's also something we probably want to measure, because the thing is, this pressure sensor looks, from what I've seen, gives us more like an exponential change in resistance, right? When you press on it, in proportion to the force. So maybe in that case, this is actually better. yeah, anyway, that's like the first draft. We actually haven't really done anything with the pressure part yet, mostly because that's far less sensitive than the position, right? Because this will determine pitch, basically, if we want to, which is, I mean, the most likely use, right, of the touch strip will be to control pitch like you would, just by fretting the guitar string. Right, so this is basically where we want the most precision. Now there is this funny thing here with the thermistor. The reason I put that here, it's not yet it's not yet on the prototype here, but basically the reason I wanted to have the thermistor here is to see if like in case we get any drift due to temperature changes, because that's gonna affect the resistors and the semiconductors, right? And even if we choose very good parts, parts that aren't very much temperature sensitive, and there is still a risk we will get drift with temperature changes. So we can put a thermistor and basically compensate for that. And to do that well, we also will need to, measure and the parameters across, across the temperature range. But that's something we can do, and then we can just compensate within our digital domain. So that would be one measurement we will get out, along with the position and the pressure. Now, originally when I built this with this MCP 6004 op amp, I just used the op amp to make the positive and negative outputs. But now we've got more signals here, right? So we have those two for position and pressure, which I originally, designed interconnect for and so on. And I basically took up all this, all of the op amps, of the 4 op amps on this chip. But now we also have the thermistor here. And also I'm using a more expensive op amp. So the thing is, actually the description here is wrong. So that's not the part. Let's see, let's edit the symbol here. This is the part. So this is as a differential driver, or like a dedicated differential op amp. Let me just find it here. Okay. Yeah, this is the part. Right, so fully differential amplifier. And that's looks like pretty much exactly what we want to drive the ADC. So so TI, I think this in this datasheet, basically that's what they recommend for from going from oh, not really. Let's see. There was like an application schematic somewhere in here. Oh, come on. Okay, something's weird is happening with my mouse here. Okay, this here. So this here is using this op amp as a buffer, and before this differential thing, right? And it's like, since we're going from single-handed to differential, we should be able to just put one and to ground, right? And the other as a buffer, and then this will make the differential output for us. All right. Yeah, like this here. So this part is nice because it has pretty much a similar, noise spec. Now this thing is very low noise. I mean, that's far under what we are getting with the ADC itself, but and it's not that expensive, so yeah, we'll try that. I'm actually waiting for the parts to arrive, and we'll make something like this. So I want to update this with the new. Oh, come on! And yet you still didn't give me the right value. I guess that's something I need to say. Okay, so yeah, so this is the thing. I still need to design the filter around it. To be honest, I don't fully understand the filter they are using here. I mean, I think it's something like a solemn key. I might be wrong. Though, is that a solemn key? So I think there's just a second order filter here, right? So you got your RC here, and then you get something here. I'm not sure about this topology here. Oh, and then you get another stage here, I guess. Is there an explanation here? Maybe the other datasheet has some more, design guidelines. This is their measurements. Yeah, that's all cool. Differential versus single-handed filters. Okay, sure. Oh yeah, there is the application. Yeah, I think that's the same filter. They are very similar. Yeah, there's like an extra resistor here, but I don't know if that. Yeah, that shouldn't make a difference. That will just roll into this resistance here. Interesting. Yeah, so we're gonna go for something like that. Just tweak the parameters to like 1.5 kilohertz, probably something like we had there. So this is for the 430 kilohertz response. yeah, so this is pretty much what we want. So we should be able to get this down with just this single quad op amp and this single differential op amp. So I'm gonna probably just make the position signal differential and the other one single-ended. I'm gonna need to see if we get any significant noise with single-ended, but the point is those things don't need so much resolution. So for the pressure sensor, that's just because it's not gonna basically, you're not gonna resolve or have basically that much control over the pressure for 20 bits of resolution, definitely not. So for position, actually, let me give you a reference of what kind of resolution this is, right? So the strip is around 50 centimeters long, so that's gonna be 500 millimeters, right? Divided by 2 to the, so let's say we get 8, well, yeah, we know we can get 18, but let's say we get 19 bits of effective resolution. That's gonna be a micrometer, sorry, yeah, because that's in millimeters, right? So that's let's just use meters, right? So we get our units, right? So that's like 1 micron, right? 1 micrometer. So yeah, that's some resolution, yeah, so in practice we definitely don't need to go to such low, such precise measurements. But again, I'm mostly doing this just because I can, right? And because I have to see if I can rather. Yeah. And this also will probably not need such a low resolution because those thermistors vary quite a bit with temperature, right? So we're gonna see enough, like much more voltage change here across degree Celsius than like all the offsets happening in the resistors and the op amps. I did a little experiment with so the EDC also has a built-in thermocouple and lets you read the temperature. So that's pretty useful actually. So you can basically create your offset and your measurements with temperature. And I did a little experiment and heated this up with a heat gun, and yeah, you do actually see a little bit of an offset added with the temp. Let me see. Actually, I had there is one. So this one actually didn't show that much because that's just like a minor temperature change. So the red line is the reading from the thermocouple, and the green one is the filtered signal with like the input nulled out, right? So that's just noise. anyway, what's significant here is the scales, right? So on the right is the scale in you know, in points for the temperature readout, and the left is scale for, so these are different scales, right? The noise is 15 to like around 18 points. So right, 3 or 4, around 4 points peak to peak. And this is like like 400 points, right, along the vertical scale. So yeah, so the temperature readings, and if we do a thermocouple like that, we'll probably probably see even more, you know, of a change across a degree. This wasn't like even controlled, so I don't know what the actual temperature change here was, but that's, and I definitely yeah, that definitely wasn't a lot. Sorry, I'm kind of getting tired, so I'm gonna cut the stream now. I did cover pretty much what I wanted to talk about, so next time we can do some actual design here, and you know, make a filter here and design a board for right, an actual board for this input section. Also, we're gonna see if that you know, switching that switch thing here is gonna be it's gonna be good or not. All right. So if you watched to that point, awesome. Thanks for staying with us, and see you next time, folks. Bubble from King Devices. Was here for you. And yeah, looking forward to do more of those. I don't know if I find that interesting or entertaining. Yeah, cheers.